Okay, finishing up chapter 18. Finally, we're down here in section J, which is about second and higher derivatives. So second derivatives, third derivatives, nth derivatives, and so on. Basically, the idea is we're going to take the derivative of the derivative and then see what we can do with that. This is going to have a lot of applications in the next two chapters. For now, we'll just focus on calculating it, not worrying too much about what it means, although I will say a little bit about that in this video. So the notation, two options here. One option is, and the one that I'll prefer to use, is going to use just multiple dashes. So I read this as f double prime of x. The book calls it f double dashed x, whatever. Y double prime. We can also use this one here. As we see down here, that's pronounced d2y by dx squared. If you're going to write in that notation, please put the 2's in the correct places. It does make a difference, and it actually has a lot to do with units, and we'll speak about that later in this video. So taking the second derivative is very easy. As I said earlier, we just take the derivative of the derivative. So here's our function. The derivative is easy to calculate. The second derivative is just as easy to calculate, right? Just using the same derivative rules over again. So there's nothing special about calculating a second derivative or a higher one. As we keep going higher, though, like sometimes writing multiple primes or dashes could be a little annoying. So I think our book tends to quit after 2. I usually quit after 3. I'm content to write f triple prime of x. But beyond that, I use this notation here, which we use parentheses to note that that's not an exponent, right? This is the fourth derivative of x. This is f of x raised to the fourth power. They are very different. Please do not confuse the two. So we can spot some interesting patterns happening now. So we saw in a previous video that e to the x was its own derivative. Well, sine of x is not its own derivative, but it is its own fourth derivative. Why is that? Well, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is positive sine. And then we would continue. So the 29th derivative of sine of x is cosine of x. And I know that without having to run through a whole bunch of calculations. I just know that this pattern repeats every four terms. Here's another pattern that we might spot. So this is using the power rule a whole bunch of times, starting with x to the negative 1. So using the power rule, we can figure out y prime, double prime, triple prime, quadruple prime. And what do we notice here? Now, I'm not combining those to make 6. I'm not combining those to make 24. Instead, I'm leaving them out as factors because I want to draw your attention to the factorials that are happening here, right? We have 1 factorial, 2 factorial, 3 factorial, 4 factorial, and the signs are alternating. The first derivative's negative, the third derivative's negative. Every odd derivative here is going to be negative. The evens are going to be positive. So the way to incorporate that into our general form is to use a negative 1 to the power of n. So that's going to have it alternate. It's always going to be times n factorial. And then our exponent there for the nth derivative, notice that the first derivative has an exponent of negative 2. The second derivative has an exponent of negative 3. 3 goes to negative 4, 4 goes to negative 5, and so on. So the nth derivative is going to have an exponent here of negative n minus 1. So that's a general form for the nth derivative of x to the negative 1. That's kind of neat that we could work that out. So here's just one application, and we're going to spend a lot of time in future chapters talking about stuff just like this. But a second derivative would be acceleration. So We talked in the very beginning thinking about what derivatives might be. We talked about the rate of change, right? Instantaneous rate of change. So if we start off with an initial function, which is speaking about position, and in this case it's the position of some object that's been thrown into the air and is under the effect of gravity. The rate of change of position would be velocity. And what's the rate of change of velocity? Well, that's acceleration. And think about their units. For position, it's meters. For velocity, which I could write as v of t, or we could call that s prime of t, the unit is meters per second. For acceleration, which we will often write as a of t, which is the same as v prime of t, which is the same as s double prime of t, the unit is meters per second squared. Think back to, we have y, we have dy dx, and we have d2y dx squared. Take a look at the denominators. There's no denominator. We have dx, where we're taking the derivative of the rate of change of position with respect to time. Our denominator all of a sudden has time in it. With respect to time squared, our denominator has time squared. Meters, meters, meters. All right, so that's what I was referring to earlier. And we know, backing up after all this, we know that the acceleration due to gravity is, it is 9.8 meters per second squared, more or less. And that's why in, like, if you're taking an elementary physics class, or even there are probably a lot of like word problems you've seen in earlier math classes about this, where again, an object is usually, you're studying some sort of parabola, right? You can see that this is a parabolic function. And it's, again, measuring its position over time. The equation that would be given to you, it always had negative 4.9 times time squared. And why is that? Well, it's because when we take the second derivative of this entire thing, the only thing that's going to be left at the very end is going to be the negative 9.8 from the 4.9 times that 2. And that's the acceleration. It's irrelevant of this first part. That's going to drop out. So that kind of had to do with its initial velocity, or something like that. I don't know. I'm not a physicist. I can never keep track of like those kinematic formulas, but I can spot the derivative here and how it's working. If you saw a question in feet, then the coefficient of the t squared would have usually been around like 16, because the acceleration due to gravity in feet per second squared is like 32.2 or something like that. So you've seen this stuff at work before, believe it or not. I want to show you this cool application of higher derivatives. So that's our product rule. I'm being a little lazy here just to keep the notation simple. I don't want to write f of x and g of x over and over and over again, but that's what f and g represent here. So our product rule, the derivative of f times g is equal to f times the derivative of g plus the derivative of f times g. Okay, great. I want to know what the second derivative of f times g is. Well, that means we're going to take the derivative of this right-hand side. And each part of the right-hand side is itself a new product rule. So we'll just do that. Here it is. So this one's going to get broken down here and here. We have f times the second derivative of g plus f prime times the derivative of g prime. And then this is going to get separated here and here. And then we look very carefully. We've got some like terms. So we combine them, and we have f times g double prime plus 2f prime g prime plus f double prime g. You might not be hooked yet. Let's check the third derivative. That means we're going to have to do another product rule here, here, and here. So we do that. The first one gets broken up. The second one gets broken up. Third one gets broken up. We once again spot the like terms. I see like terms here and here. Put them together. 1, 3, 3, 1. Now you should definitely be seeing it if you didn't at the previous step. This is starting to look like binomial expansion, right? Let's cut to the chase. Here's the fourth derivative of f times g. Could we come up with a formula for the nth derivative of f times g? This is going to be tough because we're going to need to incorporate the fact that it's a sum of a whole bunch of terms, which means we're going to need to use sigma. We also need to have a binomial coefficient, so we're going to need to be using n choose k. And then we're going to need to have a notation for taking the derivative of two different terms. So take them, if you want to work on this, pause the video right now and try it. If not, I'm going to go to the answer and we'll check it to make sure that it works. Ta-da! So the nth derivative of f times g is equal to the sum for k equal to 0 to n of n choose k times the n minus kth derivative of f times the kth derivative of g. That's a lot. Let's try just the first two to make sure that this actually works. So, well, first of all, let's try the first three, actually. What is the 0th derivative of f of g? Well, the 0th derivative means we're not taking the derivative. So this should just be f times g. Let's make sure that's what we get out of this formula. So it's going to be the sum from 0 all the way to 0. So that's great. So k is only going to be 0. So that's going to be n choose 0. I can make that 0 choose 0. So that's going to be 1 times the 0th derivative of f times the 0th derivative of g. This all comes out to be 1 times f times g. Yeah, okay, it works. Great. Let's look at the first derivative. I know what the answer to this should look like. So first, we're going to have k be 0, and then we're going to have k be 1, right? Because it starts at 0, and then it goes all the way up until we hit whatever number that is, which in this case is going to be 1. So it's k going from 0 to 1. When it's 0, then I have 1 choose 0 times what derivative of f? N is equal to 1, k is equal to 0, so that's f prime, times g, k is equal to 0, so that's just g, plus n is still 1, now k is 1. It's f, 1 minus 1 is 0, times g to the 1. 1 choose 0 and 1 choose 1 are both 1, so that gives me the first derivative. Let's just do one more. Second derivative. So now I'm going to take the sum from 0 to 2. So I need to add 3 terms together. 1 where k is 0, 1 where k is 1, 1 where k is 2. In all three of these cases, n is going to be equal to 2. So we've got 2 choose 0 times what derivative of f? 2 minus 0. That's the second derivative of f. Times what derivative of g? The 0th derivative of g. Plus 2 choose 1 times what derivative of f? 2 minus 1. That's 1. Times what derivative of g? 1. Plus 2 choose 2 times what derivative of f? 2 minus 2. That's 0. Times what derivative of g? 2. 2 choose 0 is 1. 2 choose 1 is 2. 2 choose 2 is 1. This gives us the second derivative of f times g as we saw earlier. The sigma is a little weird, but hopefully as I got into that third one, you started to see like how the numbers work together. And if you want to talk to me about that, just send me a message or talk to me in person, and we can expand more of those. It actually makes more sense, even to me, as I go through like 0 and 1. It makes less sense until I see like more terms and I have more separation in between what K and N are. Then it starts to, I don't know, kind of land in my brain a little bit more comfortably. Whoa, yuck! What do you make of this thing? Find the 100th derivative of this ugly function. Okay, there's got to be a trick to something like this, right? Of course there is. Take a close look at this function. If we were to expand it, which we are not going to do by any means, but if we were, what would be the highest degree of x? Well, what is the degree of this function? Well, right here we've got an x to the power of 70. Here we've got an x to the power of 22. Here we've got an x to the power of 7. When I multiply those three together, we're getting x to the power of 99 with a coefficient of 1. So it'll be 1 times x to the power of 99 plus other terms. But the other terms are going to have a degree of, at most, 98. So now we're going to take the 100th derivative of this. But this is all just going to be power rule, right? So we can think about simpler functions. If we have x squared, and I take the third derivative of it, well, the first derivative is 2x, the second derivative is 2, third derivative is 0. If I take really any power, and I take a derivative which is greater than that power, I'm always going to end up here, right? So the 100th derivative of this function is exactly equal to 0. That was kind of lame. Let's do a more interesting question. What's its 99th derivative? That's at least a little more challenging. So in this case, again, if we were to expand this, we're going to have 1x to the 99th. Shouldn't have erased that. Oh well. Plus a whole bunch of terms which are at most x to the 98th. So when we take the 99th derivative, all those terms are going to go away. They're all going to drop out to 0. What's going to be left from this one? Well, let's start to think about what its derivatives would have been. So as we take the first derivative, it's going to be 99 times x to the 98th. When we take the second derivative, it's going to be 99 times 98 times x to the 97. As I take the third derivative, oh, I see the pattern here, right? It's equal to 99 factorial. Clever, clever, clever. Let's close things off to just kind of easy things. First, as a fun note, maybe, we had a limit definition of what the first derivative was, which is in our formula book, and we're required to know that for polynomial functions. If you're interested, here's a limit definition for the second derivative. I doubt you'll ever need to know that, but there it is. And I'd like to quote the calculus book that I found this example in, which says, "It is an interesting fact of more advanced mathematics that there are functions f for which this limit exists at all points, but the function is not differentiable." So that's pretty cool that we could actually calculate this limit as though the function was differentiable, but you actually could not take the derivative of that function. Now, maybe I just blew your mind because so far we've just been looking at all these functions that we can take the derivatives of, but there actually are some functions that you can't differentiate at all. What does that even look like? What does it mean for a function not to be differentiable? Well, we saw in previous videos that absolute value of x, for example, we can take its derivative everywhere except when x is equal to 0 because it's got that corner there. And so corners and cusps are problematic when taking derivatives. So there is, the most famous example I can think of is something called the Weierstrass function, which looks like this. which if you were to zoom in anywhere, here we are zooming in at this bottom point here, and we just get this here. Basically everywhere, it's just corners. It's corners all the way down. I don't know what that means. This hurts my brain to think about it. I've never studied the Weierstrass function in any official capacity. I just know that it's a very curious function, which has you cannot take its derivative anywhere, even though it's continuous. You could draw this entire thing without ever picking up your pen. Weird thing. And the last thing I wanted to show you was just with calculators. If we wanted to take the second derivative on a calculator, it's just the same as taking the first derivative. We're going to go to Menu, Calculus. We're going to take the numerical derivative at a point. We always leave the variable as x. The value would be whatever the value is going to be. I don't know. I'll do 4. And then instead of the first derivative, we ask for the second derivative. And that's basically it. Let's do something easy like x cubed. That way we can calculate this in our head and just check the answer. So if our function is x cubed, the first derivative is 3x squared. That makes the second derivative 6x, which if x is equal to 4, that's 6 times 4, so that's 24. There you go. That's how to calculate a second derivative on a calculator, as long as you know what the x value is they need to calculate it at. Unfortunately, the calculator cannot get you the general first or second derivatives unless you're using a CAS. And if you're using a CAS, then you're breaking the rules for the IB. So stop that. Anyway, that's it for chapter 18. Oh my gosh. Now we're just going to jump into applications of derivatives in the next 2 chapters. This is where it gets really fun. So you need to make sure that you're comfortable with all of the rules that we saw here. Because if you're still uncertain about how to really use some of these, then when we start applying them, it's just going to be absolutely impossible. So please study, practice, ask questions if you need to. Calculus is awesome. Calculus is easy. Algebra is hard. So practice the algebra. And I don't know. Let's get some. Let's go. Woo! All right. Calculus. Boom.